Classical mechanics describes familiar motion with Newton's laws, where a force changes the motion of a particle according to force equals mass times acceleration. This works very well for planets, cars, balls, and many everyday objects because those objects usually have clear positions and paths. Electrons forced physicists to rethink that picture because electron diffraction, the double-slit experiment, and the pattern of light from atoms showed behavior that looked wave-like instead of simply particle-like. In a diffraction experiment, electrons passing through a tiny opening spread out, just as water waves or light waves spread after passing through a narrow gap. In a double-slit experiment, electrons can build an interference pattern, meaning some regions receive many electrons and other regions receive few, as if waves from two openings were adding and canceling. Atomic spectra added another clue, because atoms emit and absorb only certain colors of light, suggesting that electrons inside atoms can have only certain allowed energies. These results point to wave-particle duality, which is the idea that matter can show both particle properties and wave properties depending on how it is measured. Louis de Broglie gave this idea a mathematical form by proposing that a particle has a wavelength equal to Planck's constant divided by its momentum. In words, a particle with larger momentum has a shorter associated wavelength, while a particle with smaller momentum has a longer associated wavelength. This relationship was radical because wavelength had usually been a wave property, while momentum had usually been a particle property. De Broglie's idea joined those two descriptions and suggested that every moving particle has a matter wave connected with it. Once matter has wave behavior, physics needs an equation for that wave. Just as sound waves, water waves, and light waves each obey equations describing how they change. The wave used in quantum mechanics is called the wave function, and it is usually written with the Greek letter psi. The wave function is not a little physical ripple in space that can be touched, because it is a mathematical description of the quantum state of a particle. A simple traveling wave can be written as psi of x and t equals a times e to the power I times open parentheses kx minus omega t close parentheses. In this expression, a is the amplitude, k is the wave number, omega is the angular frequency, x is position, and t is time. The wave number measures how rapidly the wave changes across space, while the angular frequency measures how rapidly the wave changes in time. This kind of wave is called a plane wave, which is an ideal wave with one definite wavelength and one definite direction of motion. The letter I appears because quantum waves are often written with complex numbers, where I means the square root of -1. Complex numbers may seem strange at first, but they make the mathematics of waves easier because exponentials are very simple to differentiate. Euler's formula explains the connection by saying that e to the power I theta equals cosine theta plus I times sine theta. This means the complex exponential is a compact way to carry both sine and cosine wave behavior at the same time. The wave function itself is not directly measured as an ordinary physical height or displacement. The measurable quantity is the absolute value of psi squared, which gives the probability density for finding the particle near a position. Probability density means probability per unit length in one dimension, so regions with a larger absolute value of psi squared are regions where the particle is more likely to be found. This changes the meaning of a wave. Instead of describing where a particle definitely is, the wave function describes the pattern of possible measurement results. The next step is to connect the wave function with particle properties such as momentum and energy. De Broglie's momentum relation can be written as momentum equals h bar times wave number. Here h bar means Planck's constant divided by 2 pi, which appears often because circular wave motion naturally uses angles measured in radians. The matching energy relation is energy equals h bar times angular frequency. These two equations say that the particle quantities, momentum and energy, are tied to the wave quantities, wave number and angular frequency. When those relations are placed into the plane wave, the wave function becomes a times e to the power I times open parentheses px minus et close parentheses divided by h bar. This form is important because the momentum p and the energy e now sit directly inside the wave function's phase. The phase is the part of the wave expression that decides where the wave is in its cycle of oscillation. If momentum changes, the spatial part of the phase changes, so the wave's spatial wiggles become closer together or farther apart. If energy changes, the time part of the phase changes, so the wave's oscillation in time becomes faster or slower. This is the bridge from classical mechanics to quantum mechanics, because energy and momentum are no longer only numbers attached to a moving point particle. In quantum mechanics, energy and momentum are encoded in how the wave function changes. To reveal that encoding, the wave function can be differentiated with respect to position. For the plane wave, the partial derivative of psi with respect to x equals ip over h bar times psi. This happens because differentiating the exponential brings down the coefficient of x from the exponent. Multiplying both sides by negative ih bar gives negative ih bar times the partial derivative of psi with respect to x equals p times psi. This result suggests that momentum can be represented by the operator negative ih bar times the partial derivative with respect to x. An operator is a mathematical instruction that acts on a function and produces a new function, or a measurable value. In classical physics, momentum can be treated as a number for a particle with a definite motion. In quantum mechanics, the wave function may contain a range of possible positions and momenta, so physical quantities are represented by operators acting on the wave function. The momentum operator extracts momentum information from how the wave function changes in space. A wave that changes rapidly over space has a large wave number, and through de Broglie's relation, that corresponds to a large momentum. A wave that changes slowly over space has a small wave number, and that corresponds to a smaller momentum. This explains why a spatial derivative is the natural mathematical tool for momentum in quantum mechanics. The same idea gives the energy operator by differentiating the plane wave with respect to time. For the plane wave, the partial derivative of psi with respect to t equals negative I e over h bar times psi. Multiplying both sides by ih bar gives ih bar times the partial derivative of psi with respect to t equals e times psi. This suggests that energy is represented by the operator ih bar times the partial derivative with respect to t. The energy operator extracts energy information from how the wave function changes in time. A faster time oscillation means a larger angular frequency, and because energy equals h bar times angular frequency, it also means a larger energy. At this point, the wave description has supplied two key quantum tools. Momentum becomes negative ih bar times a space derivative, and energy becomes ih bar times a time derivative. The final derivation uses the classical energy equation for a non-relativistic particle moving in a potential energy field. Non-relativistic means the particle is moving much slower than the speed of light, so ordinary kinetic energy is accurate enough. The classical energy equation says total energy equals momentum squared divided by 2m plus v. In that equation, m is the particle's mass and v is the potential energy, which describes stored energy due to forces such as electric attraction or repulsion. The term momentum squared divided by 2m is kinetic energy, which is the energy of motion. The term v is potential energy, which depends on the environment around the particle. Schrödinger's key move was to turn this energy statement into a wave equation by letting each quantity act on the wave function. Multiplying the classical energy equation by psi gives E times psi equals p squared divided by 2m times psi plus v times psi. The left side, E times phi, is replaced by the energy operator acting on phi, which is ih bar times the partial derivative of phi with respect to t. The momentum part needs p squared, so the momentum operator must act twice. Since p is represented by negative is bar times the partial derivative with respect to x, p squared is represented by negative is bar squared times the second partial derivative with respect to x squared. The minus sign appears because negative I squared gives negative 1 when the operator is applied twice. Substituting these operator forms gives ih bar times the partial derivative of psi with respect to t equals negative h bar squared over 2m times the second partial derivative of psi with respect to x squared plus v times psi. This is the one-dimensional time-dependent Schrödinger equation. It is time-dependent because it describes how the wave function changes as time passes. It is one-dimensional because the position variable is only x, so the particle is being described along a line. The left side of the equation represents the time evolution of the quantum state. The first term on the right side represents kinetic energy because it comes from momentum squared divided by 2m. The second spatial derivative measures curvature, which tells how sharply the wave function bends across position. That curvature is connected to momentum and kinetic energy because tightly bending or rapidly oscillating waves are linked to larger momentum. The second term on the right side, V times phi, represents potential energy and shows how external forces shape the wave function. For an electron in an atom, the potential energy comes mainly from electric attraction between the negative electron and the positive nucleus. Different potential energy functions produce different allowed wave patterns and different allowed energies. This is why the Schrödinger equation can explain atomic spectra, because only certain stable wave patterns fit inside an atom. The equation can also be extended from 1 dimension to 3 dimensions. In 3 dimensions, the second derivative with respect to x squared is replaced by the Laplacian. The Laplacian is an operator that adds the second partial derivative with respect to x squared, the second partial derivative with respect to y squared, and the second partial derivative with respect to z squared. The three-dimensional time-dependent Schrödinger equation says I(h bar) times the partial derivative of psi with respect to t equals negative h bar squared over 2m times the Laplacian of psi plus v times psi. This version lets the wave function spread and change through ordinary space rather than only along a line. The structure of the equation stays the same. The left side gives time change, the first right side term gives kinetic energy, and the second right side term gives potential energy. The derivation shows that the Schrödinger equation is not just a random formula, because it combines matter waves, de Broglie's relations, derivative operators, and the classical energy equation. Its central idea is that the quantum state is a wave function, and the future shape of that wave function is determined by its energy. From this one framework, physics can describe electrons in atoms, bonding in molecules, charge flow in semiconductors, laser behavior, and many other parts of modern technology. The Schrödinger equation therefore stands as the basic rule for non-relativistic quantum motion. A particle's wave function evolves in time according to its kinetic energy and potential energy.